In this video, we're talking about line segments and how to determine whether or not two line segments are parallel to one another, perpendicular to one another, or neither parallel nor perpendicular. And parallel, perpendicular, or neither is all about the slopes of the line segments. And this is the exact same process we use to determine whether or not lines are parallel, perpendicular, or neither. It's no different when it's line segments or lines. It's all about the slope, and this slope formula, if we say that the slope is m, then we know that the slope is equal to the change in y over the change in x, which we can find using this formula y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. Now we've been given three different problems. The first problem here, we have two line segments. One line segment between its endpoints -1, 1 and 2, 3, and another line segment between its endpoints 2, 2 and 5, 4. So we could graph these on coordinate axes and then try to determine visually whether or not they're parallel, perpendicular, or neither. But a visual picture that looks like the lines are approximately parallel or approximately perpendicular or neither of those isn't going to prove to us that the lines are in fact parallel, perpendicular, or neither. So to prove that the line segments fall into one of these categories, we have to use the slope formula. So we're going to need to find the slope of each one of our line segments. So if we say the slope of this first line segment, the line segment that connects the points -1, 1 and 2, 3, the slope of that line segment, we're going to take the y values and subtract 1 from the other. So the y values are 1 and 3, so we're going to say 1 minus 3. And we're going to divide that by the difference between the x values. Now, since we took the y value in the first coordinate and subtracted the y value in the second coordinate, we have to do the same with the x values. Take the x value in the first coordinate, -1, and subtract the x value in the second coordinate, 2. And when we simplify this, what we're going to get is 1 minus 3, which is going to give us a -2, divided by -1 minus 2, which is a -3. And of course, we can cancel those negative signs and call this slope 2/3. So the slope of this line segment is going to be 2/3. If we look at the slope of this line segment, the line segment that connects the endpoints 2, 2 and 5, 4, we're going to say the slope is, and again, we're going to take the y value, so we're going to say 2 minus 4, 2 minus 4, and then we're going to divide that by the difference between the x values. So because we subtracted the y value in the second coordinate from the y value in the first coordinate, we have to subtract the x value in the second coordinate from the x value in the first coordinate, and we say 2 minus 5. And when we simplify, we're going to get -2 over -3, the negative signs cancel, and we get 2/3. So what we see is that our slopes are equal to one another. And when the slopes are equal, that tells us that the line segments are parallel. So the line segments are going to be parallel. Now what we can do is go ahead and graph the line segments to verify that they do look parallel, and that's a good double check. You need to calculate the slope to prove parallel, perpendicular, or neither, but graphing them is a good visual double check. So if we say take the endpoints -1, 1, so -1 is going to be here and up 1 is going to be right here. So if we say this is the point here, -1, 1, and then we graph the point 2, 3, so we'll get 2 and then up to 3 right here. We can say that this is our first line segment if we just go ahead and connect these points. Now let's go ahead and plot the second line segment. We have the endpoint 2, 2, so we find 2, 2, which is going to be right here. And then we find the endpoint 5, 4, so we come out here to 5, which is all the way on the edge of our graph, and up to 4, which is right here. And if we go ahead and connect these endpoints, what we see is that we have lines that look roughly parallel. They certainly don't look like they're perpendicular, set at 90 degrees from one another. So they look like they're going to be parallel, and that's just a good double check to verify that the slopes are in fact the same. What about this second example here where we have the endpoints -2, 2 and 3, 2 for our first line segment? Well, again, we're going to find the slope, so we're going to say m is equal to, we'll say 2 minus 2, we'll take this y value and subtract the second y value, so 2 minus 2, divided by the first x value minus the second x value, so -2 minus 3. And when we simplify, 2 minus 2 gives us 0. -2 minus 3 gives us a -5, but of course 0 divided by anything there, we're going to get 0. What about the slope of the second line segment where the endpoints are 2, -1 and 2, 4? Well, the slope there if we say the first y value, -1, minus the second y value, +4, divided by the first x value, 2, minus the second x value, 2, we're going to get -1 minus 4 is a -5, 2 minus 2 is 0, and what we see is that we have a fraction that's undefined. Whenever we have 0 in the denominator, we know that the fraction is undefined, and a slope that's undefined means that the line is going to be a perfectly vertical line. When the slope is equal to 0, we know we're going to have a perfectly horizontal line. So we have a perfectly horizontal line and a perfectly vertical line. So looking at that information, we can already say that these two line segments are going to be perpendicular. But let's go ahead and verify it by plotting the endpoints and then connecting them with line segments. So we have the coordinate point -2, +2. So if we come out here to -2 and then up to +2, we get this point right here. And then the point 3, 2, so we come out to 3 and up to 2 right here. And if we go ahead and connect those with a line, we see that this is a perfectly horizontal line between the two endpoints. And now if we take the other two endpoints, we say 2, -1, so we come out to +2 and we come down to -1 right here. And then we say 2, 4, so we come out to +2 and we go up to 4, which is going to be right here, and we connect those with the line segment. What we see is that this is a perfectly vertical line, and so because these lines are set at a perfect 90 degrees from one another, they are in fact perpendicular lines, and the slopes prove that. So again, we had a perfectly horizontal line because the slope was equal to 0, and we had a perfectly vertical line because the slope was undefined because we had a 0 in the denominator. Let's look at our last example here. The first line segment is defined between the endpoints -1, 2 and 1, -2. So if we find the slope of that line segment, we're going to take the first y value and subtract the second y value, so 2 minus -2. Then we're going to take the first x value and subtract the second x value, so -1 minus a +1. -2 minus a negative, that's going to become a positive, so 2 plus 2 is going to be 4, and then -1 minus 1 is a -2, which is going to be equal to -2. If we look at the second line segment here, defined between the endpoints 1, -2 and 2, -1, we'll take the first y value, -2, and subtract the second y value, -1, and then take the first x value, +1, and subtract the second x value, +2, and when we simplify, -2 minus a negative, these will become a positive, so -2 plus 1 gives us a -1. 1 minus 2 gives us a -1, and so -1 divided by -1 is going to give us a +1. So we have slopes here of -2 and +1. Since the slopes are not equal to one another, we know that the lines are not parallel, and since one slope is not the negative reciprocal of the other slope, we know that the lines are also not perpendicular. So in this case, we're going to say neither, that these line segments are neither parallel nor perpendicular. Now let's go back to what we just said about one slope being the negative reciprocal of the other. In this second example here where we talked about perpendicular lines, we happen to end up with a perfectly horizontal line and a perfectly vertical line. But oftentimes with perpendicular lines, that won't be the case. To determine whether or not two lines are perpendicular, what you're looking for by definition is for one slope to be the negative reciprocal of the other slope. So remember, the reciprocal of a fraction is just whatever we get when we switch the numerator and denominator. So for example, if I know that one slope, the slope of one line segment, is, for example, 2/3, if I want the reciprocal of this fraction, I just flip the place of the numerator and denominator. So instead of 2/3, I'm going to get 3/2. So then I can say 3/2 is the reciprocal of 2/3. If I make this a negative, so I get -3/2, then this is the negative reciprocal of this value here. Two lines are perpendicular, or two line segments are perpendicular, if one slope is the negative reciprocal of the other slope. So if I look at these values here, -2 and +1, if I want to find the negative reciprocal of -2, first of all, I want to realize that -2 is the same as -2 over 1, right? There's that understood 1 in the denominator. So if I want to find the reciprocal of this, I flip the place of the numerator and denominator, 1 over 2. And I would have to keep this negative sign, but when I want the negative reciprocal, I multiply this by -1, so the negative sign goes away. In other words, when you're dealing with the negative reciprocal, one is going to have a negative sign and the other will not. So the negative reciprocal of -2 is +1/2, but I don't have +1/2, I have a +1. So -2 and +1 are not the negative reciprocals of each other, and therefore I can say that these lines are not perpendicular. And obviously because the slopes are not the same, I can say that they're also not parallel. And let's just graph them to confirm that that's the case. So I have this endpoint -1, +2, so I come here to -1, +2, and I graph that endpoint. I have the endpoint 1, -2, so I come out here to 1, and I come down to -2, and I graph this endpoint right here, and I want to connect them with a line segment, which looks something like this. Then I look at my second line segment, which has endpoints 1, -2, so I come out here to 1, -2, which is again this point right here that we already plotted, and then the point 2, -1. So I come out to 2, and then I come down to -1, and I have this endpoint right here. And if I connect these two with the line segment, I get this line segment looking like this, and these look like they might be about perpendicular, but in fact, looking at the slopes, we proved already that the slopes are not the negative reciprocals of one another, so we know that they're not perpendicular. And if we measured this with a protractor, we would in fact see that the angle between them is not 90 degrees, where the angle between these line segments was in fact 90 degrees, and therefore they were perpendicular. But in this case, these two line segments are neither parallel nor perpendicular, and that's how you use information about the slopes of line segments to say whether or not they're parallel, perpendicular, or neither.